Section 7.4, Variation. Our goals for this section are to talk about various kinds of variation, including direct variation involving powers, inverse variation, joint variation, and combined variation. And we're going to be seeing most of these concepts in terms of applications. So a simple idea to get us started in the section. If you work for an hourly wage, then the amount you earn varies directly with the number of hours you work. So this statement, we have the statement that says varies directly, and some quantity varies directly with another quantity. If I let H represent the hours worked, and if I let E represent the amount earned, then I can write a model, an equation that represents this situation. And the equation could be written as E, the amount earned, is equal to K times H. The amount I earn is some number multiplied by the number of hours earned. We call this number K the constant of variation. Now, in this example, it's your hourly rate. So if you work at a job that pays $10.50 per hour, then you could write earnings is $10.50 times H. And then you can work with that. All right, so let's formalize that a little bit. Let X and Y be two quantities. We say that Y varies directly with X. Another way to say that is Y is directly proportional to X. If Y equals K times X, where K is a non-zero constant called the constant of variation or constant of proportionality. Alright, so when you see this phrase, Y varies directly with X, or some other terms, you can immediately write Y equals Kx, and then work with it. Let's see an application. The amount of sales taxes, S, on an item varies directly with its purchase price, P. Suppose a person buys a $425.50 item, and the sales tax amounts to $29.79. We're asked to find an equation of variation and to determine the purchase price of an item if the sales tax was $805. The key phrase is that the sales tax, S, on the item varies directly with its purchase price, P. Using that phrase, I can write the model S equals KP. The price varies, as the sales tax varies directly with the price. Now, I need to figure out what is this value of K for the model. So we have some information. We are told that a $425.50 item, so that's a value of P, has a sales tax of $29.79. That's a value of S. Alright, so using that, I can write 29.79 is equal to K times 425.50. I can solve this equation for K by dividing through by 425.50. I'm going to use a calculator for this. Let's try that again. Right over here. 29.79, divide that by 425.50, gives us about 0.07. So let's say that K is 0.07. So that's a 7% sales tax. So then the model that I would write is S, the sales tax, is 0.07 K. not k, excuse me, 0.07 p. S is equal to kp, and k is 0.07. That's the model that I could write for this application. Now in exercise B, we're asked to determine the purchase price of an item if the sales tax was $805. All right, so $805 was the sales tax. That's a value of S. So I can write the equation 805 is 0.07 p. To solve for p, I can divide through by 0.07, both sides of the equation. Again, I'll use the calculator. 805 divided by 0.07 is 11,500. My conclusion: the purchase price of the item was $11,500. Right, so there's an example using a direct variation. Some situations involve direct variation with powers. So again, if we have x and y representing quantities, we say that y varies directly, or y is directly proportional to the nth power of x. So we say that y varies directly with the nth power of x if y is equal to k times x to the n, where k is again a non-zero constant. So if we see the phrase y varies directly with the nth power of x, we can write the model y equals kx to the n. Let's see a quick example. Suppose m is directly proportional to the cube of h. Right there, that phrase, m is directly proportional to the cube of h. The cube is the third power of h. So that means I can write that m is equal to our constant of variation times h to the third power. And m equals 768 when h equals 4. So 768 is equal to k times 4 cubed. 768. So now I can solve for k. I just need to divide through by 4 cubed. So let's see, 768 and divide that by 4 to the third power is 12. So k is 12. And the model for this situation, the equation, would be m is equal to 12h cubed. All right, let's see an application. The distance d that a ball rolls down an inclined plane varies directly as the square of the time t in seconds. A ball takes 2 seconds to roll 20 feet. We're asked to find the equation that describes the ball's distance after t seconds. All right, so let's look for the key phrase here. The distance d varies directly as the square of the time t. The distance d varies directly as the square of the time. D is equal to k t squared. Now, let's use the other information to figure out the value of k. A ball takes 2 seconds to roll 20 feet. So that means when t is 2, d is 20. 20 equals k times 2 squared. I can solve for k by dividing through by 2 squared, which is 4. And so then k is 5. So then my model would be that d is equal to 5t squared. How far will the ball roll in 3 seconds? In 3 seconds, the distance would be equal to 5 times 3 squared. So the distance would be 5 times 9, that's 45. So conclusion, the ball will roll 45, our units are feet on the distance, feet in 3 seconds. How long would it take for the ball to roll 50 feet? Well, that's a value for the distance. So 50 is equal to 5 times t squared, dividing through by 5. That gives us 10 is equal to t squared. And applying the square root property, t would be plus or minus the square root of 10. Now, in this situation, we can't have negative time, so t would be the square root of 10. And using the calculator, we find that the square root of 10 is about 3.16. So t is about 3.16. So the ball takes 3.16 seconds to roll 50 feet. Now let's go back for a moment and consider these the two examples that we've seen, the two main examples. We had a direct variation with the sales tax, and we found our tax to be equal to 0.07 times x, whatever our input variable was. Now notice if we think of that as graphically, that's a line and with a positive slope. And if we graph this on a reasonable window, let me set my window from, I don't know, 0 to $1,000. And so then I'll set the scale. I'll set the scale to hundreds. And so x would have been in that situation with the sales tax. That's the purchase price, and then the sales tax is 7%. So minimum of 0 and a maximum of. I'll set the maximum to be 100. And I'll use a scale of tens here. And if we graph that, notice that we do get a line that is rising. It's increasing from left to right. Okay. And in general, a direct variation increases from left to right. And let's see that with the second example. We had the distance was 5t squared. All right, so 5x squared. And we know from what we've learned in the past that this is quadratic. This is a parabola opening up. And so if we only consider positive times, so let's go from 0 to 10 seconds. And then for the y's, well, 10 squared is 100, so 500 feet. Let's go from 0 to 500 feet. And again, I'll use, how about a scale of hundreds? Notice we see, again, an increasing function from left to right. So that's one thing that's important to recognize, is that direct variation increases from left to right. So if we have y equals kx, we will get a line through the origin. If we have y equals kx to the n, we will get some sort of curve from the origin and increasing. It's not always a parabola because it depends on the value of n. Okay, but generally we'll have a power that's increasing. Now, if n, I should say that this is true if n is greater than 1. If n is between 0 and 1, we haven't seen an example like that, but we would get a curve that looks like this. If n is between 0 and 1. Say, for example, a square root, right? If we had the square root of x, well, that's the same as n to the 1/2 power. So just be aware of those different situations. Inverse variation. Let x and y be two quantities and k a non-zero constant. We say that y varies inversely with x, or y is inversely proportional to x, if y equals k divided by x. And we say that y varies inversely with the nth power of x, or y is inversely proportional to the nth power of x, if y equals k over x to the n. Alright, so with a direct variation, we were taking our constant and multiplying by a power of x. With an inverse variation, we're taking our constant and dividing by a power of x. So let's see this example. Suppose g varies inversely with the cube of c. G varies inversely with the cube of c. That tells me then that g is equal to some constant divided by c cubed. Now, we're told that g is 125 when c is 0.5. So then 125 is equal to k over 0.5 cubed. Now, I can solve this equation for k by multiplying by 0.5 cubed. I'll use the calculator for that. 125 and multiply that by 0.5 to the third power, and that gives me 15.625. So k is 15.625. So then my model, my equation would be g equals 15.625 over c cubed. Let's look at an application. The force F needed to loosen a bolt with a wrench is inversely proportional with the length L of the handle. Suppose that 300 pounds of force is needed to loosen a bolt with a 5-inch wrench. Write an equation that describes the force F needed to loosen a bolt in terms of the length of the handle, L. The force is inversely proportional with the length L. The force F is inversely proportional with the length L. Suppose that that 300 pounds of force, F equals 300, is needed to loosen a bolt with a 5-inch wrench, L equals 5. 300, right, the F value is 300, is equal to K over 5. I multiply through both sides by 5, and I can write, and I find that K then is 1,500. So then my model is F equals 1,500 over L. Part B. How many pounds of force would be needed with an 8-inch wrench? So if I increase the length of the wrench, what happens? The force would now be 1,500 divided by 8? Well, I'm dividing by a larger number, right? Originally I was dividing by 5, and it took 300 pounds of force. Now I'm dividing by a larger number, 1,500 divided by 8, 187.5. So on that same bolt, an 8-inch wrench would need 187.5 pounds of force to loosen the bolt. Determine the length of the handle if 250 pounds of force was needed. So if 250 then, not 2,500, sorry, 250 would be 1,500 over L. I multiply through both sides by L, and that would give me 250L is equal to 1,500, and now I can divide through by both sides by 250, and I find then that L is 6. So the length of the handle would be 6 inches if the bolt needed 250 pounds of force to be loosened. Now let's look at a graph of that function, f equals 1,500 over L, and hopefully you recognize that as just a transformation of 1 over x, one of our basic functions back in chapter 3. So if I graph y equals 1,500 over L, so over x, and let me use the window, how about 0 to 20 on the x's, so 0 inches to 20 inches, and I'll use a scale of, how about, let's go from 0 to 2,000 on the y's. And I'll use a scale of hundreds on the y's. And so notice that this does appear to be a transformation of y equals 1 over x, where we're only looking at the values of x is greater than 0. And notice that as I move from left to right, this function, this graph decreases. So as you increase the length of the handle, you need less force to loosen the bolt. And we can maybe find a couple of the points here. If I trace L equals 5, if I trace x equals 5, there's our original point. 5 inches, 300 pounds of force. 8 inches, 187.5 pounds of force. And as the length becomes greater, right? Let's look at about a length of 18. You know, if I had an 18-inch wrench, I only need 83 pounds of force. And as you can see, as that length becomes larger, the amount of force needed becomes much smaller. Okay, and so that's what happens with inverse variation. As you increase the input, the output decreases. Let's see another example. The intensity I in decibels of a sound is inversely proportional to the square of the distance d from the sound source. Suppose the decibel level of a Beatles tribute band is 36 decibels from a distance of 50 feet from the stage. We're asked to write the equation that describes the intensity I of a sound that is a distance of d feet from the source. Let's find our key phrase. The intensity I is inversely proportional to the square of the distance d. I is k divided by d squared, inversely proportional. We're dividing by the power of d. Substitute our known information. The decibel level is 36. That's a value of I from a distance of 50 feet. That's a value of d. So 36 is equal to k over 50 squared. To solve for k, I would multiply through by 50 squared on both sides of the equation. Use the calculator here. 36 times 50 squared is 90,000. So 90,000 is k, and so my model then would be that the intensity is 90,000 divided by the distance squared. If the distance from the source is 28 feet, find the intensity of the sound. Alright, so then the intensity would be 90,000 over 28 squared. I'll use the calculator here. 90,000, divide that by 28 squared, is 114.8. Alright, conclusion. 28 feet from the source the intensity of the sound is 114.8 decibels. Alright, so now think about this for a minute. 50 feet from the stage, the decibel level was 36, and if I move closer to the stage, it gets louder. 114.8. When the distance decreased, the intensity increased. Now that makes sense if you think about, realistic situation. If you get closer to the sound, the intensity increases. If you move further away from the sound, the intensity decreases. Alright, so understand that we have to think about that differently. If we decrease our distance from the stage, from the sound, the intensity increases. If I increase the distance from the sound, the intensity decreases. Determine the distance from the source if the sound intensity is 100 decibels. Alright, so then that's an intensity level. So 100 equals 90,000 over d squared. Let me multiply through both sides of the equation by d squared. So then 100 d squared is 90,000. I'll now divide through by 100. And d squared is, let me just double check that, 90,000. Divide that by 100 is 900. And so then d would be plus or minus square root of 900. But our distance is only going to be a positive value, so distance is the square root of 900. Which is 30. Alright, so a conclusion. The sound intensity will be, I'm sorry, yeah, the sound intensity will be 100 decibels, 30 feet from the stage. And let's look at a graph of this function as well. Alright, our intensity was 90,000 over x squared. 90,000 over x squared. And so if you're only 1 foot from the stage, that would be an intensity of 90,000. So for my window, let's go from, I don't know, 0 to 100 feet from the stage. And I'll use a scale of tens. And for the y's, I'll go from 0 to 90,000. And I'll use a scale of 200s. How about, or let's use a scale of 500s. That'll give us 18 marks. All right, and graphing that. All right, so we see it very quickly diminish. So let me change the window. Let's go from 0. Let me change this from 90,000 to a reasonable decibel level would go up to 200, let's say. And I'll use a scale of tens. Alright, so again, notice we have a similar shape as in the first example. It's, as I move from left to right, it is decreasing. And again, we can find a couple of points on here. If you were 50 feet from the stage, graph, and let me trace. So right there, 50 feet from the stage, 36 decibel level. If I am 75 feet from the stage, the decibel level's down to 16. Alright, so notice it is decreasing as I move from left to right. Alright, so in general, inverse variation will decrease. It decreases from left to right. And generally, we see a graph that looks similar to this when we have y equals k over x to the n. Joint variation. Let x, y, and z be 3 quantities. We say that y varies jointly with x and y, or y is jointly proportional to x and z. Y varies jointly with x and z, or y is jointly proportional to x and z if y equals k times x times z. So let's see an application. The work done, W, in joules, when an object is lifted, is jointly proportional to the mass, m, in kilograms of the object, and the height, h, in meters, that the object is lifted. Suppose it takes 147 joules to lift a 6 kilogram weight 2.5 meters. Write a variation equation that models this scenario. The work, W, when an object is lifted, is jointly proportional to the mass and the height. So W is K m h. K times m times h. Just like we've done previously, now we throw in what we know. It takes 147 joules, that's a value for W, to lift a 6 kilogram weight, that's an m value, 2.5 meters, that's an h value. 147 is equal to K times 6 times 2.5. 6 times 2.5 is 15. 147 is equal to K times 15. I divide through by 15. Is 9.8. So then I can write my model. W equals 9.8 mh. Determine the amount of work needed to lift a box 0.5 meters that weighs 8 kilograms. The amount of work, W, would equal 9.8 times the mass, 8, times the height lifted, 0.5. 9.8 times 8 times 0.5 is 39.2. Right, so it would need so the amount of work is 39.2 joules. Determine the height that a 15 kilogram object was lifted if the work was 47 joules to lift it 1.6 meters. So 47 would equal 9.8, that's the K value, times 15, that's the mass, the weight, to lift it for 1.6 meters. That doesn't make any sense. And part C, and it was written down incorrectly, that should say determine the mass of the object if the work was 47 joules to lift it 1.6 meters. So then 47 would equal 9.8 by the mass, which is unknown, by the height, 1.6. Alright, so on the right-hand side, I can multiply the 9.6 by the 9.8 by 1.6, and that's 15.68. So 47 is equal to 15.68 m. Now I'll divide through by 15.68. So 47 divided by 15.68 is 2.997. Alright, so the mass so the object had a mass of about 3 kilograms. Combined variation. When we have a situation where direct and inverse variation occur at the same time, we call it a combined variation. Suppose R varies directly with H and inversely with P. R varies directly with H and inversely with P. Then R is equal to K times H divided by P. K is our constant, varying directly with H, multiplying by H, and inversely with P, dividing by P. And that R equals 24 when H is 1.3 and P is 5. Alright, so let's solve for K. I'll multiply by 5. So then 120 is equal to 1.3K. And dividing through by 1.3. So let's say 92.31. So then our model is R equals 92.31 H over P. Alright, let's see an application. The force F needed to keep a car from skidding on a road varies jointly with the weight W of the car and the square of the car's speed S, and inversely with the radius R of the curve in the road. Wow, okay, let's look at this again. The force varies jointly with the weight W and the square of the car's speed S, and inversely with the radius R. The force F varies jointly with the weight and the square of the car's speed, and inversely with the radius. Alright, so there's actually four variables here. The force, the weight, the speed, and the radius. Suppose that a force of 6,160 pounds, so that's an F value, is needed to keep a 3,500 pound car, that's a W value, from skidding on a curve that has a radius of 300 feet, that's R, with the car traveling at 40 miles per hour, that's S. Alright, so 6,160 then is equal to K times 3,500 times 40 squared over 300. Let me multiply by 300. $6,160 times 300 is 1,848,000. And I have K times now 3,500 times 40 square. 3,500 times 40 square is 5,600,000. Let me divide through by that 5,600,000 to isolate K. Alright, so let's see. 1,848,000. Divide that by 5,600,000. That's 0.33. So then my model is F equals 0.33 WS squared over R. Determine the weight of a car traveling 35 miles per hour if it takes 4,100 pounds of force to keep it from skidding on a road with a radius of 480 feet. Substitute what we know. It takes 4,100 pounds of force. So 4,100 equals 0.33. I don't know the weight of the car. I know the speed, 35, and I'm squaring that, and I know the radius is 480. Alright, now I have to solve for W. I will multiply through by 480. $4,100 by 480. Oh, wrong button. Sorry about that. 4,100 times 480. 1,968,000. So that's 0.33 by W by 35 squared. Now, 0.33 by 35 squared, that's just a number. Let's simplify that. 0.33 by 35 squared is 404.25. So 1968000 is, I forgot the number already, 404.25 W. And so now let me divide through by the 404.25. $1,968,000. Divide that by 404.25. And let's just round to the nearest whole number, 4,868. So W is approximately 4,868. My conclusion, the car weighs 4,868 pounds. Alright, so that concludes this presentation on section 7.3.